Those chairs up there, like what are y'all doing up there?
They have some other arrangement in the class. All right, let's begin. Welcome to CS 4510. Which one of these works? This is L10A. We're finally in the halfway point. What is the topic of today? So we have gone basically as far as we can with the Turing machine because we don't have a good grounding of all the other concepts, formalizations of intuitive principles that we need in order to proceed further. So we're now going to take a very long detour through 3 millennia of mathematics history so we can get back through everything, so we know everything, and then we can go back to talking about how to apply that to the Turing machine. Today's topic, the lecture title is Countability. But it's really a notion of what is infinity. And infinity is, an ancient and historical concept, but it's not really. It's something that we've kind of known about only in really a modern sense. So that's basically what we're going to do today is formalize the notion of infinity. Quick history. For a long time, a lot of mathematics followed the work of Aristotle and Archimedes. And Archimedes had a notion, which we may call the Archimedean principle. Which says something like the part is less than the whole. By the way, ancient Greek philosophy is not particularly impressive or anything. They were just the first people to write these things down in stone. These are really basic concepts that you already know without having anyone to tell you that they're true. You could rediscover every single ancient Greek syllogism or whatever, but we believe this, right? It's obviously true. If I have a pizza and I have 3 slices of pizza, 3 slices of pizza is less than the whole pizza, which is 8 slices. If we were to formalize this in set theory, we would say that if A is part and not equal to B, then that would imply that the cardinality of A must be strictly less than and not equal to B. Right. The problem with looking too fondly backwards among Greek is that you get stuck in a rut because Aristotle, Archimedes, all these guys made tons of errors as well. We talked about this last time when we talked about Galileo, right? Aristotle thought that the speed of falling was dependent upon the mass of the object, right? So people didn't really question this kind of thing for a long time. Galileo comes along and he discovers the following. And he calls it a paradox, but it's not really. And most paradoxes on closer inspection appear to vanish. They're simply issues of impreciseness or some sort of conflation of distinct ideas and so on, right? They're not really paradoxes. And this is also such one. But what he calls a paradox is that we may have in consideration the natural numbers. Let's say 1, 2, 3, 4, 5, right? And we may correspond to each natural number a perfect square in such a way. Right? So first off, what are perfect squares? Perfect squares are any number multiplied by themselves. What Galileo notices here is that first off, the naturals are there. Fine. Second off, the perfect squares that are there, okay? The perfect squares are part of the natural numbers, yet may be put in correspondence with the natural numbers. So what Galileo says here is that there are as many perfect squares as there are natural numbers. And he does this big treatise, he writes everything in Latin, and it appears to be the case, and if we were to use modern notation, that we have a set which is a strict subset, but the cardinality of A is equal to the cardinality of B, right? That appears to be the case. So what is his resolution on this? What he says is, okay, well, here's the final say, and there's a few directions you can take in this. He says, okay, we don't, the Archimedean principle it only applies to finite sets. Again, he didn't know what a set was, Galileo, but this is what we can correspond to, right? So any discussion about the infinite is, you have to tread very carefully around, because we have a lot of intuition about finite sets. We understand very well how numbers interact with each other, because the number is a formalization of the intuitive concept of dealing with a quantity. And we have a lot of good intuition about how that works. But some of that intuition, as we see, does not extend into consideration of the infinite. So we have to be careful when we're talking about the infinite, what is something that generalizes from the study of finite objects to the study of infinite ones. We have to be careful, does this actually work? Or does the study of the infinite go in a different direction than the way we think numbers interact, right? So it appears that infinity is not like a number, because it doesn't behave like a number, because a part of infinity could still be infinity, right? So basically this was kind of the prevailing view, not even because of Galileo, just because for a few more hundred years, because you didn't really need to deal with the infinite really in a completed sense. When you consider the naturals, you consider them in progress. They're procedurally generated, and in some ending process, in an unending way that'll never be completed, right? The definition of the natural numbers, by the way, is given inductively. First, you say that 0 is a natural number, and then you say that for any number that is natural, its successor must be natural, where the successor is equal to n plus 1, right? Because such a process is never completed, you cannot consider the natural numbers or any other infinites in totality. It's always in progress. It's unceasing, right? So to consider the naturals in a completed sense was a very different kind of thing. But that's okay. This kind of understanding of how numbers work is sufficient to do basically all the math that we needed up to that point. I mean, calculus is derived in terms of limits. So, I mean, you have a limit there and a limit here. As long as that goes before this one, you're good. Anytime you need a number, make sure you've done that enough times, and then you have the number. But this understanding of the naturals is sufficient for most of that kind of mathematics. Now, this understanding of the naturals is very different than this understanding of the naturals, which is consideration of the naturals in a completed sense, where this is some sequence of numbers, and this itself is one set consisting of an infinite collection of objects, right? So this is an infinite set, one set that is infinite. And this is an object we consider, it's the more useful definition today. Of course we do the big capital N for this for the natural numbers. And it was understood, historically you could talk about this, but you could not talk about this, right? This is like, don't do that, right? So that's fine. I mean, most of math was done that way for a very long time. Until, I mean, basically people, of course, if you tell mathematicians don't think about something, they're gonna go back and see why not, or they're gonna go try to figure it out. So along comes a guy named George Cantor, and Cantor basically gives us the modern definition of infinity, and in fact the natural numbers, and he tells us how to define them and how to work with them. So everyone was doing this, and he's like, okay, what if I do this? What's going to happen? And that's basically going to be the point of today's lecture. What happens if we consider infinity in a completed sense? So that's basically the point of today's lecture. Any questions so far? Right. So first off, what does it mean for a set to have cardinality? So Galileo here, how was he able to, how do we know two sets are the same size? How do we know in the finite way, if A and B are finite, how do we know that they have the same number of elements?
You count the number of elements?
Yeah, I mean, like yeah, I suppose. So, like, let's say A was ABC. Right? We agree that's true. Why is it true? With all such concepts, it's obvious, but like, think about your own intuition about why this is true, and tell me it. You said you can count them, right? So what you're saying is you say 1, 2, 3, then you go to the other set, you say 1, 2, 3. That's certainly one way to do it for finite sets, but it's not the only way. Yeah, you pair them up. You say, okay, well, A and 1, and B and 2 and 3, C and 3. Okay, so because then therefore there is as many as each other, right? In fact, what you could think about is a pairing between objects in the first set and the second set. Now it turns out if we just take that intuition about equality, equinumerousness of sets, that works for the infinite, right? So we just do that, do that. Right? So if you can pair up two infinite sets in such a way, then they are, the big fancy word is equinumerous, right? There's as many as one as the other, which is basically what Galileo did. Does anyone know what this kind of function is called? It's a bijection. Yeah. So we need to get, that's going to be the foundation of our definition. We say f from sets A to B is a bijection if it is surjective and injective. Let's define what those are in just a second. F is injective if for A and A prime in A, it is true that distinctness in the domain implies distinctness in the codomain. Right? So if A and A prime are distinct in the domain, then after you perform the map, they will be distinct in the codomain. Right? More usefully than this definition is the contrapositive, which is that if f of A is equal to f of A prime, that implies that A equals A prime. Right? Pictorially, an injection you should think like an injection, right? Like it injects into it. This is an injection. This is not an injection. Okay? You have A here and you have A prime here, but they somehow map to the same thing, right? That would be considered non-injective. This is an injection, it injects, it's an injective function, that's a non-injective function, right? What if we did the other way? What's the problem with this one?
It's not a function.
Yeah, it's not even a function. In fact, in the intuitive sense, this doesn't pass the straight line test, right? This is a relation only. So don't even consider that kind of case, right? F is surjective if for all B in the codomain, there exists an A in the domain such that f of A is equal to B. Everything in the codomain, and the codomain is the thing on the right, the thing post, the domain is things in on the things on the left. It's the pre. An injective, a surjective function looks like this. A non-surjective function would look like this, perhaps. Right. By definition, we consider every function to be total, and that everything in the domain is mapped. If there's something in the domain not mapped, then just that's not worthy of consideration. We require every function to be total. That is what makes this function not surjective, because there's something in the codomain that's our B that does not have an A that maps to it, right? Now, it turns out if a function is injective and surjective, it's bijective. And you should think of every bijection like pictorially like this. It's a perfect pairing. Every single thing in the two sets are paired up perfectly. And that is the intuitive notion of a bijection. We also have a theorem from finite sets. If A and B are finite, and the cardinality of A is equal to the cardinality of B, then that's true if and only if there exists a bijection from A to B. That's not too hard to prove. I've done it in 2050. I've given it even as a homework in 2050. It's not too challenging. You assume to the contrary. If one is bigger than the other, then it's not surjective. If in the other case, if the other is bigger than it, then it's not injective. Something like this, right? So this is true for finite sets. So we take it as the definition for infinite sets. So two infinite sets can be considered to have the same cardinality when there is a bijection between the two. That's the definition we'll use of, we'll use the use of a bijection to tell us when two infinities are the same, right? Rather than relying on a broken thing like the Archimedean property, we'll go to something like this, right? Questions on this definition so far? So we are concerned with a kind of infinity called the countable infinite. We say some set S is countably infinite if there exists a bijection from S to the naturals. And now what this really means is that you can quote unquote count the elements of S, right? By the way, what are some properties you know about bijections? Start throwing things at the wall. There's at least 2 or 3 things that bijections have that no other function really has. Not sure anyone remembers. That's okay. The inverse of a bijection is also a bijection. That you could prove. Here's the picture, though, not a proof. That's the bijection, and then that's the inverse bijection, right? Sometimes the inverse of a function is not even a function. And in fact, it's explicitly when the function is not injective is the inverse of a function not a function. But the inverse of a bijection is always a bijection. So we may equivalently say there exists some function not from S to N, but from N to S. It's the same thing, where G would be the inverse of F, right? The inverse of a bijection is a bijection. So either definition suffices to say that something is countably infinite. What else? The composition of bijections is also a bijection. That can be proven as well. Right? Picture makes sense. Okay, fine. Proof works. Even in the case that A, B, and C are infinite. So the composition of bijections is a bijection. The inverse of a bijection is a bijection. Right. This has a very important property that's preserved from us, which is very difficult to prove. It's called Schroeder-Bernstein, and this is not even the formal definition of Schroeder-Bernstein. This is just a useful version of it. Is that if A is a subset of B, that implies that the cardinality of A is less than or equal to the cardinality of B. Okay? That is still preserved for us using the definition of the bijection definition of correspondence. And basically the way it works is like there's some mapping from A to B, and then such a mapping would also exist. But formally proving Schroeder-Bernstein involves something with mirrors, and it's quite complicated, in fact, because you're only dealing with these functions. So let's not think about it, but we may assume that we have something like this for free. But we do not assume something like the Archimedean principle, which is that if A is a strict subset of B, then that implies that cardinality of A is less than the cardinality of B. That is no longer true, right? Because now we've seen through Galileo's example, the part can be equal to the whole. Now, but it's not true, for example, that the part could be greater than the whole. That, at least, we have confidence in. The part could be equal to the whole, but the part could not be greater. So, questions just on the definition. Okay, I'm going to give you some sets, and we're going to discuss proving that they are or are not in correspondence with the naturals. So, sometimes the definition of naturals excludes 1. Number theorists don't like considering 0 because if you say it's true for all natural numbers, they don't want to say, well, except 0, because repeatedly taking things to exponent 0 means you get non-uniqueness. Taking things to division by 0 is just a headache. You don't want to define any of this. So a lot of times number theorists will not consider the naturals to contain 0. We're in the domain of logic, set theory, and especially computer science. We need to consider 0 as a natural. All of Boolean logic relies on this. So we'll just say, let those other naturals be like this, okay? Now, how many of those are there? I claim that there's a countably infinite number of such naturals. Give me a function which corresponds our definition of the naturals with the other definition of the naturals.
or 1 and 0, and then
But what is the function? Let's say f of n takes on input n.
-1.
Other way.
Sorry, other way.
Yeah, n plus 1. But notice the inverse of a bijection is a bijection, n minus 1 would go the other way. Okay, I mean, like, you could prove that's injective and surjective. It's a quick exercise. N minus 1 equals n plus 1 equals m plus 1, n equals m, okay, done. It's injective, is everything in the domain, everything in the codomain mapped to? Yes, by the thing, the n minus 1th element in the domain, right? We give you the picture. Okay. So there's exactly as many naturals. So first thing, it's not too important that we consider 0. It's not some great mathematical shift in the definition of naturals whether we have this extra element in there, because we see there's still as many of them. So it's not a huge change for us to consider such a thing. And this is sufficient for us to demonstrate that the cardinality of the naturals is equal to the cardinality of the naturals without 0. So they are both countably infinite, right? The naturals without 1 is countably infinite. That's the first thing I'll say is that it doesn't really matter if you add this 0 here. It's just a convention that helps and not some great earthquaking change. The second thing is, what does this really tell us about infinity? You take this infinity here, it's kind of like, and I'm going to preface this as the unmathematical portion, but it's kind of like you take infinity, and that's equivalent to you take infinity, you plus or minus some constant, right? If you have a countable infinite, and you add or remove a few elements, it's still infinite. Okay, that's not very formal, so I'll just kind of surround it like that. But as we have such a more formal development of infinity, we get to make such statements, because it's like, I mean, like, this is something a grade schooler may be able to think. Like, what is infinity plus 1? I think there was some results that, like, only at age 7 do students really understand in a very formal sense the concept of infinity, in the sense of the old school Galileo style stuff, which is like there is no greatest number. You ask a kid, what's the biggest number you know? They'll say 17, and you say, is that the biggest? And they say no, and then you say why? And they say, well, you could take that and add 1 to it, and now that's a bigger number. That kind of notion of infinity, people understand at that young of an age, right? So if you say something like this, of course this is poor mathematics, don't do this. You can't say infinity is equal to infinity plus 1. But if you could, it would be true. So it's not false, certainly. Question so far? Okay. What about the even numbers? Let's consider 2n to be, say 0, 2, 4, something like this, right? First off, it's not, a second thing we note, it's like the naturals without 0, it's a part of the naturals, so it's a subset. What is a bijection, let's say, from the naturals to the evens? Yeah. Okay. I think they're doing construction in the other room. So, yeah. Bijection, yeah, obviously. No division by 0 issues, we're all good. Okay. Let me just. Yeah, okay. Okay, fine. So there's as many even numbers as there are natural numbers, right? What can this really tell us in terms of laws? It's like infinity is equal to any constant c times infinity, right? If you take 3 infinity, 4 infinity, that's just infinity. Now, again, not formal, but intuitive, like our use of the bijection corresponds to this, okay? Why are the perfect squares, let's do another one. What about the perfect squares? I don't have a name for this set. Let's say 1, 4, 9, 16. Why is such a set countably infinite? give me a bijection from the naturals to this set.
N is equal to n squared.
Yeah, almost, but in the way I've written it, and this is not important at all, this is, I don't know why I didn't do this. 0 is not considered a perfect square, I guess, on this thing on the board.
N is equal to n plus 1 squared.
Yeah, you move it over and then you square it, so that would be, again, notice compositions of bijections is a bijection. We compose that bijection with Galileo's, essentially. This is just the formal version of Galileo's argument, right? Okay, let's consider something harder. What are the integers? The integers, anyone know why it's called Z? German. Do you know the German, you remember the German word? I don't. Okay, that's fine. Anyway, the integers are positive and negative natural numbers. So, let's see, negative 2, negative 1, 0, 1, 2. It goes infinite in both ways. This is difficult. I need a bijection. I claim that although there's twice as many, so these are all subsets of the naturals, and we've put the part in correspondence with the whole. Fine. This is no longer a subset of the naturals. In fact, the naturals are a subset of it. This is something larger than the naturals. I claim that something larger than the naturals can be put in correspondence with the naturals. There appears to be at least twice as many integers as there are naturals. But I still claim that there is a bijection you can give me from the naturals to the integers.
You do it with the evens and the odds where like 0 still goes to 0, but then like 1 would go to 1 and negative 1 would go to 2. Would it have to be?
Well, let's see. Let's write it out. It was 0, 1, 2, 3, 4, 5. Okay. What does 0 map to?
0. 1, negative 1, 2, negative 2, 3.
Yeah. Okay. We need to convince ourselves this is a bijection. Okay. So here's how I'm going to convince you. Right. Every number is hit exactly once in such an ordering, so it is definitely a bijection. If I were to write this out as an actual function, if I wanted to actually prove the surjectiveness, what is this? This is minus n over 2 if n is even, and then n plus 1 over 2 if n is odd. Is that right? So I'm double check that. That sounds right. Okay. Now you could then go through some case to actually prove this is injective and surjective, but this is what the actual map is. And this is sufficient for us to know now that there are exactly as many integers as there are naturals. Even though there's twice as many of them, that's still the same amount. So we know now that the naturals are countably infinite. Questions on that? Okay, let's do, there are other sets that are in consideration in higher mathematics. The other one is going to be the rationals. So you can define, let's just only consider the positive rationals. It's not necessarily true that, the argument we're going to make will hold for all the rationals, but let's just consider the positive ones. These consist of integer ratios, such that a comma b are both, let's say, naturals. The actual definition says a and b are integers. But for simplicity, let's just suppose they're naturals. And what else? There's one other thing that's important. Yes. Okay. Now, then, unlike the other things we've discussed, the rationals have a lot different you could do with the rationals than you can do with any other set. I think most of calculus does not actually require the reals, and in fact could be defined upon the rationals. Why? The rationals have a very important property called density. So density says that between any two numbers of the set, there exists another number of that set. For example, it is false that there exists a natural between any two naturals, right? But it is true that there exists a rational between every two rationals. Between every two rationals, there is another rational. Why is that true? Yeah.
And take their average.
Yeah, and so what would the average be? It's going to be like A over B plus half of C over D minus A over B, right? Something like that. You go to A over B and then you go halfway of that distance. That's going to give you a rational number. You FOIL and factor that, you're going to get some rational number, okay? So that's a very different kind of infinity. So while the infiniteness of the naturals appears discrete and in distinct steps, it is the rationals also have a different property, this density property. It's not true for the naturals or the integers. Between every two rational numbers, there's a rational number, right? Between every two rational numbers, there's a rational number. Between every two rational numbers, there's a rational number. Between every two rational numbers, there's a rational number. Between every two rational numbers, there's a rational number, and so on, right? So in some sense, the infinity not just goes outward, but inside as well. That makes it kind of complicated to immediately find a bijection. For example, what would the first natural number be? Let's suppose we were in consideration of a bijection, right? We're gonna have a hard time. What's the first? Give me a rational. Yeah.
1.1.
So what is that? What is that? That's 11/10, okay? What's the next, is that the first, in an intuitive sense, the first rational? What's a more first rational?
101 over 10.
Isn't there things between those? Are you skipping them?
Probably, yeah.
Yes, we need to somehow,
1 over 10?
1 over 10, okay. But I don't know, like,
1.
any procedure I think you could come up with, I feel like that there's something missing in any explanation of an ordering. So what we're gonna do to find there is an explicit bijection, in fact, it's known. It's just a quadratic function, it turns out, but I don't remember it off the top of my head. So I'll give you the other one. First we need a simple ordering lemma. Let's call it ordering lemma. If the elements of S can be uniquely ordered, then S is countably infinite. What do we mean by a unique ordering? We mean, first off, every element appears in the ordering. Second off, we mean every element appears exactly once in the ordering, right? So every element shows itself, and every element appears once in the ordering. That's what we mean by unique, and that's what we mean by ordering. Consider that that is an ordering of the integers. We get 0, 1, -1, 2, -2, 3, -3, right? Every integer appears in such a place exactly once, and every integer is in the ordering. So this would imply that without having to do any of the bijective stuff, and we can prove it, right? So let's prove this lemma real quick. We give a bijection from the naturals to the set S, right? Let the bijection, if the ordering is A0, A1, A2, those are the elements of S. Consider the bijection that just maps the integer I to the element in the ith spot, right? The injective and surjectiveness will almost follow immediately. Suppose we prove the function is injective, and we will do it the same way here with the contrapositive. If f of a equals f of a prime, that implies a equals a prime, right? So what we're gonna do is here's how we're gonna prove injectivity. If we prove that f is injective and surjective, we've proven that f is a bijection, right? So to prove injectiveness, let f of I equal f of j. Well, what do we know by definition that f of I is gonna map to the element in the ith spot, so this is just gonna be some a of I, and this is gonna be some a of j. What do we know now? What's the next step? Yeah.
Proving surjectivity?
Well, we're not finished with injectivity. We want to prove I equals j. But if we know a of I equals a of j, what follows? What should follow?
I is equal to j.
Well, why? I agree. The uniqueness. A of I and A of j are two elements in the ordering. So if A of I is equal to A of j, and the elements, of course, by definition, the elements in a set are unique. So if A of I equals A of j, it can only be the case that I equals j, because otherwise the elements would not be uniquely ordered, and some element would appear twice in the ordering. So it must be the case that I equals j. They're not distinctive. Otherwise, that would contradict the uniqueness. Okay? Surjectivity. Let A of S, let A be an element of S, such that A is equal to A of I. So it's in the ith spot, right? What element in the natural maps to A of I? Yeah. Since the ordering goes over all elements, it's injective. This function is injective, right? For every S in A, for every A in S, it's somewhere in line. So that spot that it is in line is the number that maps to it, QED. We've shown it's injective, we've shown it's surjective. Since it's injective and surjective, therefore it's bijective. So, really simple lemma. To prove something countably infinite, just find a unique ordering of elements in the set. Every element must be in this ordering, and every element must appear at exactly once in the ordering. If we can pass those two checks, then we have a bijection. Done. Implicitly so. Questions on this lemma? Okay, let's give an ordering of the naturals then. Excuse me, of the rationals. Suppose I were to arrange them in such a grid. Let's say 1, 1, 1 half, 1/3, 1/4. And let's do the other way. Let's do 2 over 1, 2 over 2, 2 over 3. 3 over 1, 4 over 1, 5 over 1. And here we go 2 over 2, 2 over 3, 2 over 4. Here would go 3 over 2, 3 over 3, 3 over 4. Here would go 4 over 2, 4 over 3, 4 over 4. Here would go 5 over 2, 5 over 3, 5 over 4. Okay. So let's just, if we arrange them in such a way, we can still try to find a unique ordering by looking at them in such a layout, right? So suppose we took an ordering, for example, 1 over 1, 1 over 2, 1 over 3, 1 over 4. If we just try to go this way, unfortunately, such an ordering would not be unique. Excuse me, it would be unique, but it would not hit every number, right? So, for example, 2 would never be hit, 3 would never be hit, 3 halves would never be hit, and so on, right? So if we go through the top, we would not hit every number. Similarly, if we go down any column, we would go 1, 2, 3, 4, but we would never hit 1 half, or 1/3, right, and 2/3. So those would also not hit every number. So we need some way to move through such an infinite lattice to hit every number. Has anyone seen this before? Does anyone have any conjecture? Yes. So here's the first thing. We're going to compose anti-diagonals. What that means is we're going to go in this order. You go a little bit and then you make a U-turn. There you go. Okay. Cool. Every number is hit. There's a problem. What's the bug?
There's some duplicates along the main diagonal.
There's in fact many duplicates. That's definitely, every diagonal in fact has duplicates. 3 halves is also 6/4, and so on, right? So unlike a natural number in which it has a unique representation in any base, The rationals are also not uniquely represented. And in fact, even in the negative case, -1 over -1 is considered to be equal to 1 over 1. But those are two distinct ways to write the same number, right? So there are many distinct ways to write the same number. And so what that means is, although this is a total ordering, it is not unique. Several numbers are hit several times. How can we fix this? Yes?
Force all the rationals to be, the numerator and denominator to be co-prime. Or you can just identify every single rational with every single multiple of that rational.
It is true that every rational, in the positive sense, can be, has a reduced form, but then I don't know how to fill in the table in such a way. For example, how would I know in such a way that which number comes in the 27th spot? If we compose anti-diagonals by reduced form, it's not immediately obvious. Although such a thing would work. Just get rid of the duplicates, right? Yeah, so instead of getting rid of duplicates in the table, let's get rid of duplicates in the injection. So compose anti-diagonals skipping duplicates. So what that means is you go 1, 1, 2, 1, 1, 2, then you go 1, 3, you skip 2 over 2, and then you go 3, 1. Then you go to 4, 1, yeah, you hit that one, you hit that one, you hit that one. You come back, you skip that one, you skip that one, and you skip that one, and you hit that one, and so on, right? So all you have to do is say I'm going to skip duplicates, and suddenly it doesn't, now it's a unique and total ordering. Why is this still a bijection? I mean, like, so let's say someone gives you a rational and say, where in line is this rational? You find its reduced form, and then you just simply compute such a process until it appears in the ordering. And then you keep a counter and you say, it's in the 27th spot. Done. QED. So this is a proof that the rationals are in fact countably infinite. There's exactly as many rationals, positive rationals in some sense, as there are natural numbers. But the case that the rationals are negative is okay because it's the same as we did the integers. You could take the positive and negative rationals and then interlace them, right? Questions on this argument? Yes?
Would you also need to prove that there is infinite coprime pairs?
As I've worded it, I don't need to do that because I just skip anything that's duplicate.
Yeah, but you could skip and left only finite elements left. You don't know that yet.
No, I could say that the rationals are certainly infinite simply because there is an infinite subset. And the infinite subset would be 1 over I for I is a natural, except for 0. So it would be the first row, for example, is an infinite set. Everything in the first row must be hit. Because
yes.
yes. That's a good point though. More questions? I think maybe we've seen this before. Vsauce stuff. Pop quiz. Why is it true that the Cartesian product of the naturals with the naturals is countably infinite?
It's just like doing the rationals. It's when you just have two.
Do the same thing, don't skip anything. Pairs of numbers can be put into such a lattice and enumerated over in an easy and equivalent way. There's other ways to prove that as well. Pop quiz, what about the rationals, Cartesian product with the rationals, Cartesian product with the naturals. Yeah.
So theorem that's like the countable union or countable product of countable sets is countable.
I'm asking you to prove that theorem.
Just go 1 from 1 and 1 from the other, and then 2 from 1. You do the same kind of diagonal thing but in higher dimensions.
So if you were to arrange the triples of numbers into a 3-dimensional lattice, you claim that there is a path that can traverse every element of 3-dimensional lattice. That sounds non-trivial, and I believe it, absolutely. I guess you would do slice by slice in some way, and then you complicate it. Here's a simpler argument, okay? That is countably infinite, we just said. Order those elements in some way, and then arrange the pairs of elements in columns and rows, and then the composition of bijections is a bijection, right? So you would arrange on one you would basically project the 3D thing to the 2D, where one axis is not 0, 1, 2, 3, 4, but is in fact according to whatever the bijection is for this set, right? This does conflate the idea, and it's every mathematician does this, but when we say something like this, sorry, a triple like this, we are actually saying a pair of pairs, right? Those ideas are conflated all the time, right? It's not very important. Okay, cool. So Cartesian products of countably infinite sets are countably infinite. More questions on this one? So it appears that you could basically, unlike any other number, infinity has many like Plato-like properties in the sense that you could just kind of play around with it and anything really goes. And so there's this guy named David Hilbert. He'll come up more often, but it might have been his retirement address or something. He gave an analogy called Hilbert's Hotel. So Hilbert's Hotel says, suppose you have an infinitely tall hotel, right? And it has infinitely many rooms. I'm not going to draw that, but just suppose, okay? Okay. Now the hotel is completely full. It's infinitely tall. It's booked. There's a conference in town or something. A guy walks up and he says, I would like to reserve a room. And even though the hotel is booked, they say, no problem, sir. We'll find you a room. They tell him to take room 0, and they tell every patron in the hotel, if you are in room I, please move to room I+1. So this guy in room 0 is going to move to room 1. The guy in room 1 is going to move to room 2. The guy in room 2 is going to move to room 3, and so on. Everyone will settle down in a new room, and suddenly the 0th room will be empty, making space for the first guy. So in some non-intuitive sense, a full hotel can accommodate another guest, right? Fine. The next thing is that a countably infinitely long bus of countably infinitely many passengers arrives. Right? And they say, we're here for a conference, we would like to be accommodated into the hotel. They say, all right, no problem. We can assign each of you a room. They tell every patron and the guest in the room, if you are in room N, please move to room 2N. So the guy now in room 0 is going to stay there. The guy in room 1 is going to move to room 2. The guy in room 3 is going to move to room 6, and so on. So now the hotel is half empty. The guy in room 1,000,000 unfortunately has to walk really, really far because he's got to move to room 2,000,000. But the guy in room 2,000,000 has already moved. So that room is now empty for him to move into because the guy in room 2,000,000 has gone to 4,000,000 and so on, right? So now all the odd numbered rooms are empty. They say, all right, each of you can be assigned into such a room. Fine. Now suppose that there are a countably infinite number of conferences in this city, and that a countably infinite number of buses arrive, each with a countably infinite number of passengers. How can the hotel accommodate such a number of passengers? There are now infinitely many buses, each with infinitely many passengers. Yes?
This is just a guess, but would you start moving people from room I to I squared? Or is that the same as multiplying by?
I mean, so I guess the goal here is like, here's an example of a bad answer. We move the people into the first bus by taking everyone in and doubling their number. So they would move to but then the people in the second bus, we just repeat that. The problem is that process would be ad infinitum because there's infinitely many buses. So we could not stop assigning numbers to people. So I would ask if there's a point in time we could stop assigning numbers to people. Every person may be assigned a number, and that's it,
you need a bigger infinity to label the rooms?
Surprisingly, no. You can do it, all of these buses, I claim, can still fit in the same hotel.
Can you do it with the diagonals where you do like the first guy and then the first guy from the second bus and then the second guy from the first bus and then like that?
Sure, that's one answer. Tell everyone to come out of the hotel and line up out here. And then they go, okay, you guys are gonna go in the hotel in that order and fill up the rooms. That would work. Each person knows what room they're assigned to. Fine. There's another way though. There's another way that's simpler perhaps, but it leaves many of the rooms empty. Here's what you do. You could tell everyone in the hotel to move to the power of 2. Say if you're in room I, move to 2 to the I. And then if you're in bus J, move to, and in the kth spot, move to J plus 1 to the kth room. Something like this. So for example, these guys are all gonna move to powers of 2. These guys are all gonna move to powers of 3, 9, 27, and so on. These guys are gonna move to powers, primes. These guys are going to move to powers of 5, powers of 7, and so on. So each one is assigned to a unique room, but for example, no one is currently in room 6. But all these people could be put into the hotel in such a way, right? So this would be, for example, 2 squared, 2 cubed. This would be 3 squared, 3 cubed. This would be 5 squared, 5 cubed. And by properties of prime numbers, no two people would be assigned to the same room. Everyone definitely gets their own room. Now there are many empty rooms. Not very, I don't know if that's good or bad, but yeah. Questions?
And it has to be primes because if it wasn't just primes, there would be like duplicates or.
Yeah, we get it. It's easier to explain it if it's primes, but it's not the simplest way to do it. There's definitely other ways that can do it. The diagonal way has the property that there are no empty rooms. And in fact is a better answer. But here at least we know explicitly if you're in which bus and which spot in which bus, you know which room do you go to. Yes?
There are only finitely many buses, right?
No, that's the thing. There's countably infinitely many buses.
I don't think that works because I thought about what I said, and if you have a countable Cartesian product, that actually injects to the power set of the naturals.
What is a countable Cartesian product?
Like if you n cross n cross n countably many times.
We'll prove a variance of that 3 ways, but still convince yourself that each individual is in a bus with a finite number and is in line in that bus in a finite number. And there's a difference between these 2 sets versus the union of this. Those in fact being very different. I agree that this is not countable, but I'll prove to you 3 ways this is, which is the next thing we'll do in fact. So you'll see in a second, it's what the difference between those 2 things is. And that's why working with infinity needs to be formalized, because there are many hairs to split and it's very fine-grained. Basically, Cantor took up this argument because people were arguing about infinity in many ways that were not, that were intuitive, but intuition did not exactly work. And there are many subtleties that end up carrying over or not carrying over. So let me quickly prove to you, I was going to prove countable sets, countable union, countable sets, and so on is countable, but instead I'll just prove this 3 ways. So let n, and we'll let the naturals be greater than or equal to 1, and we'll call it star, consists of terminating sequences of integers. And it's important that the sequences terminate. So this consists of things like 1, the empty sequence, 20, 20, 21, 30, 30, 36, 2, whatever, right? Okay, these are all sequences. They're finite in length, and each element of the sequence could be a natural number greater than or equal to 1, right? There are 3 proofs that such a sequence is, and just for simplicity, let's just ignore this one. Doesn't really matter, we know that we have a finite K. If you add a finite element in, it's fine. Let's prove that such a set is countably infinite. I'll show you 3 different solutions. The first is, let A of I be the subset of this, which only considers sequences which sum to 1. So, excuse me, which sum to I, right? So, what is the cardinality for any I of A of I? I'm looking for a very large upper bound and not a distinct answer. Not quite. I mean, how many sequences sum to 30? There's 30 by itself, and then there's 15, 15, 10, 10, 10, 5, 6, 7, something like this, right? There's a lot of sequences, but importantly, finite. For each I, the number of sequences that sum to I is finite, right? How many sequences sum to 1? That one. How many sequences sum to 2? That one and that one, right? So we know that the naturals, the sequences of naturals greater than or equal to 1, terminating sequences of naturals, is actually equal to this union, I equals 1 to infinity of A of I, right? And in fact, if I does not equal J, then we know what about AI, what do we know about AI intersect AJ? Yes.
There's no overlap.
Yeah. No sequence can sum to 2 distinct things, right? Fine. So, given this, give me a total ordering, a total unique ordering of this. We didn't prove countable union, otherwise I would just throw that at it. But give me a unique ordering of sequences. Here's the answer. First you order A1, A2, A3, and then you order each AI by some ordering. You can always certainly do that because each AI is finite, right? So then you compose the orderings together and you'll get just some ordering of all the sequences. So this would be the first sequence, the second sequence, the third sequence, right? The fourth sequence would be that, and so on. That is a total ordering. By our ordering lemma, we've proven it's countably infinite. Now, there's a little bit of detail that should be filled in there, but I'm running short on time, so I'm going to go to the next solution. 2, this is more of a Gödel way. Suppose that we are considering a map directly of the sequence itself, A1 to say AK, and let us map such a sequence to prime powers. Right? For example, this would be 2 to the A1, 3 to the A2, 5 to the A3, to some finite largest prime number. Why is such a function injective or surjective? Or either or both? Yeah.
I would say they're both because since those are prime numbers, every product is unique.
Every number can be, this basically will inherit it's called the fundamental theorem of arithmetic. Every number greater than or equal to 1 has a unique prime factorization. I guess 1 doesn't because you could have every number greater than or equal to 2, let's say even. And 1 is not prime. So, it's injective by the fact if the output of the 2 sequences is equal to each other, then they have those 2 numbers are equal. They have the same prime factorization, so they have the same prime powers, right? So, for example, if you said 2 to the A1, 3 to the A2 equal to 2 to the B1, 3 to the B2. It could only be the case that A1 equals B1 and A2 equals B2, right? And so on. So it gets injectiveness. Does it get surjectiveness? It doesn't matter, actually. It turns out you don't need injectiveness. You don't need surjectiveness for countably infinite as long as you're going into the naturals. F is some function which takes these sequences and will map it into, let's say, the natural numbers. But it's not surjective. It's not surjective, right? Even though F is injective, since F is injective, it is bijective to its own image. And the image of the function is the thing that it maps to. But what do we know about the image? The image is just a subset of the codomain, right? The things that are mapped to is called the image, right? The image, being a subset of the naturals, is enough because although it's injective to the naturals, it's bijective just trivially to the image of the F. Now, what do we know about the image of F? It's a subset of the naturals. It's a subset of a countably infinite set. By Schroeder-Bernstein, F is going to be trivially bijective to a subset of a countable set and therefore is countable. That's all we need, it turns out. You don't even need bijectivity, you just need injectivity if you go the right way. Okay? I'll give you one final proof of this fact. And it follows from more basic principles. At the lowest level, cognitively, what is the difference between sequences? Let's say I gave you two sequences and I asked you to tell them apart. Yeah.
The contents.
The contents are different. That's an answer appropriate for, like, let's say an 8-year-old, but let's say I want a 5-year-old answer. Yes, the elements are different. How are they different?
They don't look the same.
They don't look the same. Yeah, I mean, what doesn't look the same? The numbers don't look the same. The first number is different than the first number of both, right? The answer I'm looking for is the sequences are different because they look different. That's going to motivate our final little lemma that helps with proving countable infinite. Sets are countably infinite. This is called the typewriter principle. If the elements of S can be uniquely described by strings, then S is countably infinite. So if you can uniquely describe the elements of a set by strings, then the set is countably infinite. Much more powerful than the ordering lemma. Proof, consider a function S from S to sigma star, such that F is the two-string function. For example, F of the previous sequences would map to a sequence of symbols that encode that sequence. Brackets, commas, everything, right? I claim that F is an injection. Why is F an injection? Yeah.
Uniquely maps.
Yeah, in fact, if F of A is equal to F of A prime, let's say, we know that the string description of A is equivalent in a string sense to the string description of A prime. So it could only be the case, because this two-string mapping is unique, that A was equal to A prime. So it's injective, right? So we know that the image of F, this is always true, but the image of F is a subset of sigma star. And F is bijective to, it's injective into sigma star, but then it's bijective to its own image, which is a subset of sigma star. Why, all we need now is to prove that sigma star is countably infinite. Why is sigma star countably infinite? You can't actually use the typewriter principle to prove sigma star is countably infinite, but you can use anything else. But the definition of the typewriter principle requires the use that sigma star is countably infinite. Why is sigma star countably infinite?
So you have a finite alphabet?
Sure, but why does, give me any other like bijective reason.
You can do, since the alphabet is finite, you can do the thing with the grid where you like
Yeah.
pairs of diagonals.
The problem is that a string can have length like 1,000,000. There's a little difficulty there. Give me a unique ordering of the strings. Yeah, anyone?
You map it to the naturals?
Yeah, sure. What's the map?
Oh,
There's a problem if you just do binary strings to binary numbers because strings can have leading zeros. So there's not necessarily injective, yeah?
You can sort strings lexicographically.
Lexicographic ordering. QED. That's the correspondence you put in the natural. Sort the strings lexicographically. Lexicographically means length comes first, and then if two strings are the same length, you compare them by the ordering of the alphabet that you decide, right? So it's like alphabetical, same thing. So since sigma star is countably infinite, and F maps the set into the string description of the objects of that set, then it's injective into a countably infinite set and is therefore countably infinite. This is sufficient for us to say, therefore, that S is a corresponding from naturals and is therefore countably infinite. QED. Done. Technically, we should also require that S should be infinite in general, because this would not be true in the case that S is finite, for example. Questions? Typewriter principle will come very much in handy, and it's probably the easiest way to prove something countably infinite. All right?